This is using reduced row echelon form. And on your calculator, it would be called RREF, to solve large systems of equations. Okay, so let's say that we have a system x plus y plus z is equal to 10, negative 2x minus z is equal to 5, and minus y plus 5z is equal to minus 10. Okay, so that's a system of 3 equations for 3 variables. The first step is you have to create an augmented matrix for this system. And to do that, you need to get all the variables on one side of the equation and all the constants on the other side. I guess I already have it set up that way. So start by getting all variables on, let's say, on the left side. Of equations, and all the constants alone on the right side. Then for a system of n equations with n variables, create a matrix with n rows and n plus 1 columns. Okay, so the system that I made up above had 3 equations for 3 variables. So we have 3 rows and 4 columns. Okay. Choose an order for the variables. And put the coefficients of the variables in order in the first n positions. Okay, so for the system that we have, the variables are x, y, and z. I'm going to call the first row X. So the first column is going to be X, the second one is Y, and the third one is Z. That's the order of my variables. I didn't have to choose it that way. I could have made it Z, X, Y, or whatever. You just have to be consistent as you do it. And now the rows represent the equations, and for each equation, I'm going to write the coefficients of these variables. So the first equation says 1x plus 1y plus 1z. Okay. So 1, 1, 1. The second equation says negative 2x, 0y, negative 1z. So negative 2, 0, negative 1. And the third one says negative y, negative 1y plus 5z. So negative 1, 5. Okay. The last position is the coefficients. Or the constants. So in the first equation, I have 10. The second one, I have 5. Yep, negative 10. Okay, so that's called the augmented matrix. Once you have that entered in your calculator, and let me point out before I say that, so what would have happened if I didn't get the constants alone on the other side of the equation? If I'd left them all on the left side of the equation, I would have entered negative 10 for the first equation, negative 5, positive 10, and you get the wrong answers. You actually get exactly the opposite answers. So those need to be alone on the right side of the equation. Then your calculators, and I think this is true of all the TI calculators, have a function RREF, and you can just run that on your augmented matrix. And it'll give you back a reduced row matrix that looks like this. So it's going to be the same size still. It's going to have ones down the diagonals and zeros in the other spots. And then your last column is going to be the calculated variable values in your chosen order. So the value that comes out here is going to be your X value, your Y value, and your Z value. Could somebody figure out how to run that and tell me what those values are? I didn't do that problem. Okay, wait, sorry. Negative 2.7, 12.3, 0.45. Okay. Well, this was a pretty small system of equations. It would have been faster in this case to just do substitution probably, but once you get up to 6 equations or something, this is a lot faster than trying to do it on your own by hand. And definitely when you get over 15 or something. Also, a nice thing about this is it's programmable. So, you know, if you ever end up doing statics for some company or for some research project or something, you won't be doing the calculations by hand. You'll be writing computer programs that do the calculations, and this is a way that's, you can systematize this. So let's do an example now with sort of a lot going on. So let's say we have this incline where this angle is 30 degrees. And we have a 1 kilogram cart connected by a cable to a 3 kilogram cart. And then the cable is attached to a mast that's hanging. Oh, no, this isn't a mast. Don't draw that. This is connected to the ground. Okay. And then there's one more thing going on. There's a 2 kilogram mass sitting on top of the 3. And we want to know what are the cable tension, and all the contact forces. Between the bodies. We're assuming that there's friction here. Okay, so how are we going to do this? Yeah, so we could try to piece it together in a way that we can solve for these things one by one. But the approach that I'm going to take in this class is let's just draw free body diagrams for each of those 3 bodies, see how many variables we have, see how many equations we have, and not worry about like trying to figure out, can we lump these things together, not lump these things together, that sort of stuff. Okay, so let's start with a free body diagram of the 1 kilogram. There's a weight force. 1 kilogram times 9.81 is 9.81 newtons. And now that we've dealt with the weight, we have to go around the boundary looking for where the surroundings make contact with it. Okay, so starting at the bottom, where is there contact between the 1 kilogram object and the surroundings? What? The incline, yep. And so that's a normal force because that's a frictionless contact. So that means it's perpendicular to the surface toward the chosen body. So this way. And I'll call that N1. And if I keep going around counterclockwise, I get to the cable between the 1 and 3. A cable force is parallel to the cable away from the chosen body. So I'll call that T1. And then keep going around. And the last place that there's contact with the surroundings is where the other cable is in contact with it. So that's this way. And I'll call that T2. Well, this is a problem where it might pay off to use a rotated coordinate system. But let's not. Let's just use a regular coordinate system. Like this. Well, the weight force is easy. That's in the direction of our negative y. But the cable forces and the normal force, we have to think about those directions. All right, so how are we gonna come up with unit vectors for those? That's what we need. So if this is the coordinate system, what we know to start with, yeah, we have that 30 degrees. So I'm going to draw the vector that is shown to be 30 degrees, in the picture. What we're given is that this vector makes an angle of 30 degrees with the negative x axis. Okay. That's one of the directions we want. Another direction we want is exactly opposite that. So I'll draw one like this, exactly opposite. That means that this has to be 30 degrees. And then the last one, that normal force, is perpendicular to both of those. So it's like that. And now we just have to come up with those angles. So to go counterclockwise from the positive x-axis, how do you get to this one? Well, you could go all the way around counterclockwise, or just call it negative 30. So for this one, we'll use a theta of negative 30. For that normal force direction, our theta, so how are we going to get that? Well, you can go minus 30 to get there. Now you're pointing this direction. And now we'll go plus 90 to get there. So minus 30 plus 90 is plus 60. And then the last one, you could, well, it's 180 to the negative x axis, and then backtrack 30, so 150, or you could think of it as 60 plus another 90, same thing either way. And so now we have all those angles. Now we can go to Newton's second law. And Newton's second law says, so we have to put each one of these four forces in Newton's second law. We have 0, negative 9.81. Then we have the normal force, which is at 60 degrees. So that's N1 times cosine of 60, N1 times sine of 60. Then the cable force T1, that angle is negative 30, so we have T1 times cosine of negative 30, T1 times sine of negative 30. And then we have T2, that angle is 150, so T2 times cosine of 150, T2 times sine of 150. What's the acceleration? 0, yep. So that's what we're always going to have in statics. And so we have an x equation that says, let's see, cosine of 60 degrees is 0.5. So we have 0.5 N1 plus 0.866 T1 plus negative 0.866 T2 is equal to 0. I'll just make this minus. And we have a second equation that says negative 9.81 plus 0.5 N1 minus 0.5 T1 plus 0.5 T2 is equal to 0. Can we solve for any of these variables? No, so we're just going to set this aside. What we're heading towards is building up this big system of equations. We'll keep track of the number of variables, keep track of the number of equations, and if we hopefully get the equations to catch up with the variables, then at that point we'll solve for the whole system. So here's our first equation, 1. Here's our second one, 2. For variables, we have N1, T1, and T2, so 3 variables. And now we'll go on to the second one. I guess just to go in numeric order, I'm going to go to the 2 kilogram one next, but it doesn't matter what you do first. Okay, so a free body diagram of the 2 kilogram. All right, well, there's a weight force. It's 2 kilograms, so 2 times 9.81 is 19.62. And now we're going around the boundary of the 2 kilogram, looking for where the surface, the boundary makes contact with the surroundings. Is there anywhere that happens? And the only place is the contact with 3, right? What type, how would you describe that contact? It's a friction contact, and so that means that it's a totally unknown force vector, okay? So I'm going to draw that as two components of a vector, and I'm going to give it the name force on the 2 by the 3. Yeah. Yeah. Thank you. Okay, sorry about that. Okay, well, this one, since we don't have any vectors with known directions at funny angles, we can go right to Newton's second law here. So Newton's second law says F23x, F23y plus 0, negative 19.62 is equal to zeros. And so we get one equation that says F23x is equal to 0, and one equation that says F23y minus 19.62 is equal to 0. So that's our equation 3 and 4. And for variables now, we have what? N1, T1, T2, and now these two components, I'll just write it as a vector F23. So that's 1, 2, 3, and then this one is 2, so 5. And you might think, like, well, this one, we already know that F23x is equal to 0, right? So you can get rid of that equation, get rid of that variable, and say that we have, now we only have 3 equations and 4 variables. And that's fine, that's totally right. I tend to find it easier to just keep them all until the end. But you can fiddle with that on your own. But you see what I'm saying there? It's not like we're, I mean, I'm writing it out as if we're still trying to solve for this, but there's the answer right there. Well, actually, here's the answer right there for that one too. I'm just going to keep them all and fill out the matrix as if we don't know them, and it works fine. Any questions about that? It's the friction and the normal force combined. That's all it is. It's just the contact force with the thing underneath it. So, you know, like in physics 1, the contact force is a vector, and you break it up into a normal force and a friction force. In this case, we're just leaving it as a vector. We don't care about what's normal force, what's friction force. And so we don't, because we're not dividing it up into normal and friction, there's no reason to use a rotated coordinate system like you did in physics. No, it's only the contact force. Because if you look at the picture, that's the only, you know, there's nothing else going on at the boundary except the contact with 3. Okay, so now we'll go to free body diagram of the 3 kilogram. And there's a weight force. That's 3 times 9.81, so 29.43. And now starting at the ramp, we're going to go around the boundary. There's a contact force, a frictionless contact force coming from the ramp. I'll call that N3. And notice that I tried to make it clear that those two are not parallel to each other. Okay. And keep going counterclockwise, and you get to the top. And there's a friction contact at the top. So that's the force on 3 by 2. But we already have a variable force on 2 by 3. So instead of introducing 2 new variables, we're going to set this equal to negative F23. That's Newton's third law, lets us do that. Okay. And then the last force is the cable between these two, which that tension force is what I called T1. Any questions about that? All right, well, we have to figure out a couple of directions. So here's the coordinate system. We have to figure out the angle for that. Well, really, that's the one that's given. So, you know, we know that this angle is 30. So we know that theta for this is 150. And then we need the normal force. Which is perpendicular to this. So you can think if you go from here, you go 150, you're pointing that way. Now backtrack 90, so subtract 90, and you get 60. Well, we've already had that angle, I guess, but. So theta is equal to 150 minus 90, so 60. So Newton's second law says 0, negative 29.43. Plus N3 times cosine of 60, N3 times sine of 60. Plus T1 times cosine of 150. T1 times sine of 150. And then add on negative F23x, negative F23y. And that gives us 0.5 N3 minus 0.866 T1 minus F23x is equal to 0. And then the second equation says negative 29.43 plus 0.866 N3 plus 0.5 T1 minus F23Y is equal to 0. That's equation 5 and equation 6. And now let's think about variables. We have N1, N3, T1, T2, and the vector F23. So that's 1, 2, 3, 4, 5, 6. And so now we know we can solve this system. By the way, is there any possible way that we couldn't solve this system? We have 6 equations and 6 variables. What would cause that is that you would have one or more of your equations would be linear combinations of some of your other equations. So we have 6 equations, but if it happened to turn out that they weren't all independent, then there wouldn't be an answer. And the way it would show up, it depends, the different calculators display it differently. But one thing to look for is in reduced row echelon form, your answer has to have these. So these are the only things you care about, right? But if you look at this first square matrix, if it doesn't say ones and zeros in this pattern, something went wrong with the calculation. Okay, so now to solve this system, we have to write out the augmented matrix, and we're going to enter in each of these equations one by one. Notice that I left everything on the left side. So like for equation 2, we're going to write the 0.866, the negative 0.5, positive 0.5, but this constant is going to be positive 9.81. If you don't do that, if you leave them all like this, for all of them, you get the negative answers. If you do it for some of them, you get random answers. So you have to make sure those are on their own side of the equation. Okay, so we have 6 equations and 6 variables. So we need a matrix that's 7 across and 6 down. Okay, so that's 7 columns. And then we need 6 rows. And now we have to choose an order for these variables. I guess I'll use the one that I have here. So the first variable will be N1, and then N3, and then T1, T2, F23X, F23Y, and the last one is the constants. And now we can go equation by equation. So equation 1, for N1, we have 0.5 of those. For T1, we have 0.866 of those. And for T2, we have negative 0.866. So 0.5 here, 0.866 here, negative 0.866 here. and everything else is zeros. Everybody with me on that? Then for the second equation, for N1, we have 0.866. For T1, we have negative 0.5. Do I have these? I think that's right, yeah. For T2, we have positive 0.5. And for the constant, we have positive 9.81. And the rest are zeros. For equation 3, N3, we have, where am I? For equation 3, the only thing we have is a 1 for F23x and zeros everywhere else. And then equation 4, F23y is 1. The constant is positive 19.62. And everything else is 0. Equation 5, N3 is 0.5. T1 is negative 0.866. And F23x is negative 1. And everything else is 0. And then equation 6, T1 is positive 0.5. N3 is positive 0.866. F23y is negative 1. And the constant is positive 29.43. And then zeros. And if you go through reduced row echelon form, it'll give you the same size matrix. And it'll look like this. It'll have ones down the main diagonal. It'll have zeros in all the other spots until you get to that last column. And the answers will be, so it's going to give the answers in the order that we chose them to be in. So this is going to be our N1, N2, sorry, that's an N3, T1, T2, F23x, and F23y. And the answers should be 8.50 for the first value, so that's N1. N3 should be 42.48. T1 should be 24.53. T2 should be 29.43. F23X should be 0, and F23Y should be 19.62. Yeah, so it is cool, right?